So I already have discussed differential amplifiers and why these differential amplifiers are important. What are the different details of differential amplifiers? So today I'll start with a two-stage amplifier, a two-stage operational amplifier, better to say. So when you say the operational amplifier is two-stage, I already said previously that operational amplifiers has three-stage. First is the first stage gain, then you get second stage high gain, then you get buffer, right? But when I say two-stage amplifier, we generally don't consider the buffer thing. So first high gain, whatever I said, and then we use a high swing stage. So I have shown here, first one is a high gain stage, and then you pass it to an high swing, which has possibly a little less gain. Okay, so in this case we don't consider the buffer circuit. Buffer circuit are basically the output drivers, so it decides the output of the whole operational amplifier. However, in this case we are not considering the buffer circuit, so we will see how a two-stage operational amplifier look like. So this is the circuit. Now if you see, the circuits are becoming a little complicated, right? However, this is the internal circuit of a two-stage amplifier. After that we will move into the symbol of operational amplifiers. Just to give you the idea of a two-stage amplifier, I have drawn the circuit wherein you can see that there are total of 4 MOSFETs here in the differential stage, and then you have 2 single stage CS amplifiers. Okay. However, for an operational amplifier, once I said that minimum number of transistors required are 22 if you consider everything, the 3-stage and all the possible circuits. However, depending on your design, it may rise up to 30. So the number of transistors for an operational amplifier will be somewhere between, say, 25 to 30 or 22 to 30. Okay. Although it depends on the design that you are doing. Now if you see the two-stage amplifier, it has a differential amplifier in the middle, which is connected to single stage amplifiers in both the side. So whatever output you are getting from this differential stage is the input to the output stage. And in case of output stages, the driver transistors are PMOS and NMOSs are the load. So if you see, these are the driver transistor. In case of second stage, they are PMOS devices. However, your load is in this case NMOS device. Now if you look at the first circuit, it is providing you 2 outputs, Vout1 and Vout2. So it is known as double-ended output. However, in case of the right circuit, this one, there is only one output. So it is a single-ended transistor. So you can get a two-stage double-ended, a two-stage single-ended transistors or single-ended amplifiers, better to say. Okay. So two-stage double-ended amplifier, two-stage single-ended amplifier. So if you look at this circuit, the first stage differential amplifier output V1 is going to the second stage single stage amplifier in the M5 transistor, in the driver transistor. So essentially whatever gain you are getting from here, say this gain is A1 and the gain of the single stage is A2. So previously also I once said that in that case you will get a total gain of A1 into A2. Okay, so this is one kind of amplifier which actually provides you a very high gain, because now it is getting multiplied. Say from A1 you are getting 10 to the power 4, from A2 you are getting, say, in fact 10, consider it 10, but it is increasing a order higher. The gain is increasing by an order. Order means it is increasing at least 10 times, right? Now let us see what will be the VO1 output for this differential amplifier. It will be minus GM1 into R01 parallel R03, because this is R01 is associated with M1, R03 is associated with M3 into Vin. This is your Vin, right? Now VO2, similarly, this one will be minus GM2, because this is the driver transistor, so it will be minus GM2 R02 parallel R04 into Vin, right? Now if you look at Vout1, this VO1 is now input to the M5, the second stage. So just consider this part, forget about the other circuit. If you consider this part, you have a V01 input here, then your Vout1 will be minus GM5. Remember, here the driver transistor is GM5 and your source is common, so it's a common source amplifier. So for common source amplifier, the gain is minus GM5 into R05 parallel R07. This is your load, so the output resistance of this transistor will come in parallel in the output side. If you remember the equivalent circuit which I showed previously, it is very clear that your Vout1 in this case will be minus GM5 R05 parallel R07 into VO1, because VO1 is the, or V01 is the input this time. Replace the value of V01 over here. You will get, so for your Vout1, it will be minus GM1 R01 R03 and you have GM5 R05 R07, so it will be plus in this case, okay, it will not be minus. So your Vout1 will be something like this. So what does that mean? That means you are multiplying the gain from the first stage, which is differential amplifier gain, into the gain of the second stage into Vin, right? So your AV1 gain, Vout by Vin, will be GM1 GM5 R01 parallel R07, R05 parallel R07, R01 parallel R03. So you got the gain which is equivalent to A1 into A2, right? Similarly for AV2 also we will get similar expression. In this case, if you see for AV2, that means this side, you will get Vout and your driver transistor is M6, so you will get GM6 associated with this. This is GM6. Then in this side you have driver transistor M2, so you will get GM2. See, GM2. Then the output resistance M4 and M2. The output resistances associated with M2 and M4 will come in parallel, so it will be RO2 parallel RO4, RO2 parallel RO4, and then you have M6 and M8, so it will be RO6 parallel RO8. So this is your expression. Just target whatever is the driver transistor, the GM value associated with that will come, and then find out what is the load along with the driver. So the output resistance of those loads will come as a parallel to the output resistance of the driver transistor. So this is the expression that you will get for AV2 as well. Now for single-ended case, this one, the expression will be similar, but for just one end, because you don't have the other end. So in this case, if you can see, M2 M4 and M2 is this thing, so you can get an expression of this. This will be GM2, not GM1. So your M2 is driver transistor, so it will be GM2 into RO2 parallel RO4, GM5 RO5 parallel RO6. Okay, So if you see this circuit, you have a current source, right? Now when you replace this current source with a current mirror, you can get n number of current sources associated with different circuits, right? Because in a chip you cannot put a source inside. Generally the chips are very small. Generally, if I consider this kind of circuit, it will be few in size, width and length. However, for you will get little bigger chips, but they have lot of devices. For this kind of circuits, the chip size will be in and in that case, putting source inside the chip is not possible. But even if you take power lines from this chip, you need lot of lines. So what generally people do is, I already have shown you one current mirror. They use the current mirrors to replicate the source, because in current mirrors, if you remember, you put or set the bias in this side, you'll get a similar output in the similar current in the output side. Now if you put them in parallel and vary the W by L ratio, you will get different current sources at the same time. So you can compare, you can make one pin as a control, or one pin for the biasing, and you can put lot of different biases inside the circuit. So this is generally what we do. For discrete circuits it is possible, because you are putting it in a breadboard and things like that. So it is possible in a discrete circuit, but in integrated circuit things become different. Okay, so just to give you an understanding how we place these current sources or how we place these biases inside the circuit, I just told you. Generally current mirror is the option that one can explore. Now there are 3-stage op-amps, which I already told once previously, where you have main gain stage, second gain stage, and then you have a buffer stage. Okay, so buffer stage actually gives you the output current. So your requirement for output current is generally higher, because higher the output current, I once told, if you replace this with a capacitance, if the output current is higher, it will charge faster, right? Which also helps in improving the speed of your circuit. So if your impedance is very large, then you also need higher current. So this is one of the requirement in case of op-amp. But if you look at the input side, what will be your input resistance for op-amp? If you look at the circuit here, this is your input, right? So your input resistance is basically the oxide sitting in between. So input resistance will be very high, right? From the circuit itself, it is evident that your input resistance will be very high, maybe tens of mega ohms and hundreds of mega ohms. But I have said that you need a higher current. If the current here is higher, what will be your output resistance? Output resistance is proportional to 1 by IDS, or whatever you say, the output current, right? So if you increase the output current, your output resistance is going to be low. So this is a characteristic of op-amp, that it provides high input resistance and low output resistances. This is characteristics of op-amp: high input resistance, low output resistance, and gain is very high. So you have high gain, high input resistance, low output resistance, which is the characteristics of an op-amp. Okay, so this one is to remember. However, if you replace this by a BJT, if it is a BJT based op-amp, for MOSFET it is very high. Even for BJT, what do you expect? Because in BJT you place one REE here, right? This REE comes in the output side. So when I say output resistance here, that means the output resistance seen from the output side of the amplifier, it's not output resistance of the transistors, they are very high. However, if you see the entire amplifier in consideration, that will go down. And in case of BJT, what I was saying, you have a VB junction, right? This will be VB. VB junction is connected to RE, and that RE appears in the input side as 1 plus beta times RE, and beta is generally very high. Beta in this case is gain. So in BJT case also, you will get a high input resistance, right? So for BJT and MOS both, you have high input resistance. For OPAMP, low output resistance. For OPAMP, and gain is generally very high. We already have seen it is A1 into A2. So the gain can be of the order of say 10 to the power 4, 10 to the power 5, and in best case it may go even higher. Okay. Now let us see different characteristics of OPAMP. So one of the major characteristics of OPAMP is input offset. What does that mean? So if you look at the circuit, if you look at this circuit of OPAMP, so if you put V in and V into, that means if you put the input equal to 0, your output should be 0, right? But in practice, you will see that if your input is 0, V in is 0, you get certain amount of output which is not desirable. So we call this as offset. So this is your input offset. Even at input equal to 0, you have some output. That means you have a input offset. Now, why does that happen? This happens because of the mismatch between the transistors. Even if you are making this in an integrated circuit, there can be a mismatch of W by L value. The sizes can be different. In certain cases, the VT can be different. The threshold voltages of the transistors can be different. So many transistors are attached, right? So if there is any mismatch in the circuit, you will find that there is an input offset present in the amplifier. So in that case, to get rid of this, what you do? You put an external source based on the offset value, whether it is positive or negative. You choose the value of this source so that at input equal to 0, your output is 0. Now in practice, do you put source directly? Definitely not. What you do is you put a resistive circuit like a voltage divider and connect these 2 points. You decide your R1 and R2 value, connect these 2 points to the input side, so that by changing this R1 value, you can set your offset point. Okay, you can nullify your offset. So just put a resistive circuit inside and decide what will be your R1 and R2 value, and you just nullify your offset. Okay, this is what we do in circuit. So if you see the plot, what will be the worst offset possible? The worst offset possible will be the highest output divided by AOL. Output by gain is actually your gain, actually your input, because if you look at the equation says that V in is equal to gain into V out, right? So, it is other way around actually. It's like V out is equal to gain into V in. This is what we know. Your V in multiplied by gain is your V out. So your V in will be V out by gain. Now the maximum possible V out divided by gain will be your worst possible offset. Your maximum output will be VDD or VSS or minus VSS, whatever you say. This is your maximum output. So divided by the gain is your worst case V offset. Your output cannot be higher than VDD, because if it is going beyond VDD, you are reaching this flatter side and your gain becomes 0. Your gain becomes 0. If your input is going, if your output is going beyond that, your gain becomes 0. If gain becomes 0, you don't get anything. So your highest output possible output is VDD. Okay. Now if you look at the offset, This also can be because of noise present. Now if it is the reason, if your offset is because of noise, then it may happen that you are not getting an very systematic offset. That means sometimes maybe offset positive, sometimes negative, then it becomes a difficult job for a person to nullify. If it is systematic offset, then you can put an external load or you can put some resistive circuit in order to nullify it. But if it is a random offset because of noise present, you cannot very easily nullify the offset. In that case, you have to take some extra measures. The second important thing for OPAMP is CMRR, common mode rejection ratio. Now in this case, the common mode rejection ratio is defined as minus 2 log differential gain by common mode gain. Now why this common mode gain come? Again, we have seen previously, if your current source is not ideal, you'll get some sort of common mode gain. If there is mismatch present, you'll get common mode gain. So here also you get CMRR, common mode rejection ratio. Ideally you want this to be very high. Okay, you want common mode gain to be 0 because common mode gain actually amplifying your noise. Common mode gain will amplify anything present in common in both the inputs. In general case, you will find noise is the only signal that is present in both the inputs. So it comes as a common mode and gets amplified if there is any common mode gain. Okay. So apart from this, we also have power dissipation. Now power dissipation is also a very important factor. Now it depends on the total voltage into the currents flowing through the circuit. These are all parallel currents, IDS1, IDS2. So what does that mean is, if you have a circuit like this, you know your total voltage is VSS minus VDD minus VSS is your total voltage across, and whatever current is flowing, this vertical component IDS, IDS1, IDS2, if you add them and multiply this with the voltage, maximum voltage, you will get your power dissipation. So ideally you want your circuit to be a low power circuit, so your power dissipation should be low. There is another term which is known as power supply rejection ratio. Now this basically means that if there is any variation in your VDD and VSS, you don't want that variation to affect your circuit, but your VDD and VSS variation will directly affect your DC biasing, and if DC biasing is fluctuating, then your GM will fluctuate, then your R0 will fluctuate, and all AC parameters will get fluctuate. All AC parameters will vary with time. So what exactly you want is this variation should be as low as possible. So this is known as power supply rejection ratio. So you define this as AOL, the gain, divided by V out by V plus. V plus is the variation in the VDD voltage. Similarly, for PSRR minus, it is AOL divided by V out by V minus. V minus is the variation in VSS. For VDD you say it V plus, for VSS you say it V minus. Now these type of variations are very influencing. Okay, so if this variation is very high, your circuit may not work properly. In that case, one way to get rid of this is connecting a capacitance in parallel to this VDD. So what this capacitance will do, this capacitance will reject some of the frequency components that are coming from the mains. Okay. However, this is one way to solve the problem. You will find in many circuits they put in capacitance or capacitor in parallel when the inputs or biasings are there. This is basically to avoid this kind of variations. However, in high frequency variations, or if there is different frequency components in the circuit, then you may not able to nullify those variations like this. So you may need a lot of capacitors because this is corresponds to only one frequency component, right? Or a band of frequency components. So this is not that straightforward if the variation is really serious, but this is one way you will find that people use. Okay, and then you have another term called slew rate, which is also in characteristics of operational amplifier. And what does that slew rate mean? I also discussed previously that slew rate generally means that V out by dV out by dt. That means how input is influencing the output. So if you have a current flowing in the output, previously also I have discussed once, if this ZL is an capacitor, so you want to know how fast this is getting charged, right? So generally you want this to get charged as fast as possible. So your output influence is defined by dV out by dt, which is also known as slew rate, So it is basically ISS by CL. I already have discussed previously this term. Okay, so these are the parameters that one has to take care of. Okay.